Oh, that's easier.
Okay, so
You see.
I'm gonna stop it right here.
Yep.
So send your answer if you did not yet.
25.
You can error right and more numbers.
So
Oh,
I
that's
have
weird.
the highest percentage for 4 and 3, for 2, and the highest is for 2, and then 121%. The others are minor, 112 is a 13%. Okay, so let's see which one of those are right. So the electronic transition one, which is the green arrow in there, is the absorption. Definitely it's absorption. It's going from low energy level to high energy level with the lowest wavelength. So I have to check all the absorptions that we have. So we have 1, 3, and 5 as absorption. And the green one is the one with the highest energy because it's going from n equal 1 to n equal 5. The one with the highest energy, it's definitely have the lowest wavelengths. So 1 is right because energy and wavelengths are inversely proportional to each other. So 1 is right. Let's go to 2. The electronic transition 3 is the absorption. Yes, it is absorption because we're going from lower energy level to a higher with lowest energy. So comparing 1, 3, and 5, which 3 of them are absorption, yes, it is the one, the absorption with the lowest energy. So 2 is right also. So 1 and 2 till now are right. The electronic transition 4 is the emission. Yes, it is emission. We're going from higher energy level to lower with the highest frequency. So I have to compare all the emission together. I have 2 as emission, which is the red arrow, and 4 as emission. Yet the one with the highest energy is 2. That means and energy and the frequency are proportional. So no, the number 4 is not the emission with the highest frequency. It doesn't correspond to the highest energy emission in this graph. The electronic transition 2 is the absorption. It's not absorption, it's emission, so 4 is wrong. So the right answer is 1 and 2. Both of those are right, and 3 and 4 are wrong. So by this, we've done from the Bohr model of atoms, which say, okay, there is a nucleus, there are protons, the electrons are around the nucleus. If you excite those electrons that are around the nucleus in a certain level, they're going to go from one level to the other in a quantized way. That means from n equal 1 to n equal 2, from n equal 2 to n equal 3. Now, what we're going to get started with what we call the quantum model. What we can get started with is the newest model of the atom, and that was proposed by Schrödinger. It's a little conceptual-wise, it's a little bit conceptual, so I'll try to make it as simple as possible. It's a hard thing to understand. Even chemistry major students sometimes have a hard time to understand the quantum theory. So let's get started with, so it may contradict or it may not seem exactly the same as the Bohr model. It's a little bit more advanced. So if you hear me saying something which is contradict with whatever I said on Monday, that's okay, because both theory, the quantum theory is the new theory of how we look to the atomic structure. So it's done. The theory was proposed by Schrödinger. The theory says that, okay, the electron is not a particle. It is not only a particle that is orbiting around the nucleus. No, that's not the electron. The electron, in addition that it is a particle, it has a wave property. It's wave and particle. So this is the first hard part, is to put in your mind or to conceptualize that something is a particle and a wave at the same time. The easiest, closest kind of example to that, just imagine a boat in an ocean, and that boat is moving inside the ocean. It is particle, but at the same time, it's making a wave. So this particle has wave and particle properties at the same time. So, in other words, it's hard to tell where exactly is that particle, especially the electron is very small, and it has both particle and wave property. Now, usually the Schrödinger described the electron in what we call the trajectory or the wave function of the electron. That means, okay, it's a description of where is the electron, and it has this, we use this symbol which is called the psi, that defines the system of the electron. Now, let me explain it. For example, if I take a ball and throw it this way, physics-wise, classical physics, we can know the trajectory. It's either a projectile or a free fall or any of those. We can say x or y equal x plus something. If a car is moving, you can say, oh, it started A, it ended B. So it's easy to write the trajectory. It's easy to do a function, then kind of put on the function x, y, where is it exactly, and from where you figure out where is the particle, like the ball, or any other thing, or a car or something. But since the electron is tiny small and it has both particle and wave properties, it is hard to write a trajectory. It's hard to give an equation and just begin plugging in numbers and know where is the electron exactly. Okay? So psi is just a description of the matter, but it has no physical meaning. It's not the same when we say y equal x squared plus 2 or any of those functions. It doesn't mean anything. It's just something to describe the kinetic, the potential energy of the electron inside the atom. Now, don't worry, don't panic. Those are the kinds of equations that Schrödinger deal with to get to, no, don't worry. You don't have to understand any of those. All what I'm trying to say is that the Schrödinger equations are they use differential equation and at the same time matrices to solve those very big equations. And Schrödinger, maybe all his time, he could have only solved the electron in hydrogen atom. This is all what he did in all his career, is just to describe the energy and where is the electrons inside a hydrogen atom. All what I'm trying to say is a very complex mathematics that we wouldn't talk about. Instead, what I'm going to do, I'm just going to tell you what are the results of all these equations. What did we get to? What did we learn from all these, solving all of these equations? So, not required. Okay? So, what Schrödinger said, it is impossible to find, since the electron now have a wave and a particle property, it's hard to know, to determine where is the electron exactly inside the atom, and it is hard to determine its velocity. Either you can determine the velocity of the electron inside the atom or its position, but not both of them at the same time with a good certainty, with a good accuracy. Definitely you can assume, but it's not with a high accuracy. And the way that he explained it, if you type Schrödinger on any browser, the first thing that you're going to get, Schrödinger cat. And I'm going to explain what does that mean. So Schrödinger tried to explain the fact that what he was thinking about and why he claimed the theory or proposed his theory. He said, okay, let's say I have a box in here, and it is a non-transparent box. I put a cat inside that box, and let's say I injected that box with a certain chemical, that chemical gonna make a certain alarm go off, and when the alarm go off, there will be something else released. And at this moment, that this gas that's gonna be released may kill the cat. Now, I'm outside the box. I have no idea what's going inside that box. I can't know for sure, for a high accuracy, where exactly is the cat in that box, and I don't know if it is dead or alive. I have no inquiry, and this is what we have. We don't know where is exactly the electron. I don't know the velocity of the electron. There is no way to figure out where it is. So instead, he said, okay, you know what? I don't know where it is. Where is the cat, and if it is dead or alive? But for a good certainty, for a good accuracy, I can calculate the probability. Where is the probability to find, how much is the probability to find that cat dead or alive, and where exactly inside this box? Does that make any sense to anybody? If it makes sense to you, raise your hand. If not, and don't feel shy. I mean. Okay, that's good. So it is the same idea as running a casino. So in a casino, the manager knows for sure at the end of the day he's winning. But does he know how many, or she know, he or she? Does he or she know how many people gonna come to that casino that day? Does he know at table one how many they gonna win, or how much lucky is that person that's gonna sit there and how much he gonna win? No. All what they do in casino to make sure that they are winning at the end of the day is a probability. They calculate the probability. What is the probability that somebody is gonna come and win all the money that we have? It's maybe 0.00000.00. So at the end of the day, they know whatever happened, they calculated the probability, and they know what's going on, that at the end of the day, this is the highest probability is that he as a manager is winning. Okay, and this is what Schrödinger said. I can determine where exactly is the electron at this time, at this moment when I'm sitting there. But all what I can give you for a high guarantee is the probability, the highest probability. Where is the highest probability to find this electron? And from now on, whenever we talk about orbitals, about SPD, which we're going to talk about in a minute, we're talking about the highest probability to find the electron. This is where the highest probability to find the electron, if not where the electron is exactly. So the idea that you have from high school, this is the nucleus, and electrons are in orbits, and the orbits looks like that, is wrong. It's not wrong. We don't know where is the electron. All what we know is the highest probability to find the electron is somewhere in this space that we're going to talk about soon, which are the subshells. Okay, so the bottom line of all those equations that we saw, that the Schrödinger equation talk about psi. Psi is the wave superimposed upon the radial trajectory of a particle orbiting around the nucleus. In other words, it's just a description of where is the electron. Psi square is what we're gonna depend on, and psi square is the probability in a region space where the electron is likely to be found. So all what we're gonna talk about from now on is not psi, it's psi square, which is the probability. Where is the highest probability to find the electron? Where is the probability to find electrons around the nucleus? So the orbitals that I'm gonna start talking about in a minute, I'm not gonna repeat myself every time I'm gonna say orbital. I'm gonna say, oh, this is the highest probability. But from now on, when I tell you orbital, all what I mean, or subshell, or orbital, all what I mean, that the highest probability is that the electron in that kind of an orbital, but that doesn't eliminate the idea that the electron can be outside that orbital or in another place. Okay? Now, the quantum theory yielded four things. It's going to give us idea about four things. How close is the electron to the nucleus, the type of the orbit, the size of the orbit, and the orientation. where exactly, how it is oriented, X, Y, or Z. And the quantum theory yielded 4 numbers. It yielded 3 quantum numbers. They are called N, L, and ML, and MS was followed by Schrödinger theory. But the main 3 were those 3 quantum numbers, and this is the 4th quantum number there. Now we're gonna learn what exactly N mean, L mean, ML mean, and MS mean. Okay? So we're gonna start with the first quantum number, which is N. So the principal quantum number N, this N is called the principal quantum number. So from now on, when I ask you what is the principal quantum number, you have to know directly that it is N. N is any integer greater than 0. So it can be 1, 2, 3, 4, 5, 6, etc. And N tells us how close. It is an implication. How close are we to the nucleus, or that electron is to the nucleus? And it tells us the energy, because how close are you to the nucleus, it tells you the energy. So for example, the first shell, which is very close to the nucleus, that's N equal 1. That's N equal 2, that's N equal 3. So mainly the N tells you the principal, it's the principal quantum number. It tells you it's an integer between 1 and above. It can never be 0. It tells you how close is the electron to the nucleus and the energy. Okay? Now let's talk about the second quantum number, which is L. Now, from now on, the L and ML gonna depend on each other. So the L depends on the N, the ML gonna depend on the L. So the L is the angular quantum number, and it represents the subshell shape. So we said that N equal 1, N equal 2 are the shells. Inside each cell, there is a subshell, and this is what L describes. So L is any number greater than 0, and so it can be 0. It's equal 0 or above, and it can range from 0 to N minus 1. So that means it depends, L depends on N. So it depends on which shell are we, the L, it would represent, the L will be different. As an example of that, we're gonna take, for example, for N equal 1, L can be any value between 0 to N minus 1. So 0, N minus 1, N equal 1, 1 minus 1, so it is 0. So in N equal 1, we have L equal 0. It's going to be more clear when we go to N equal 2. In N equal 2, L can be any value from 0 to N minus 1. In this case, N equal minus 1 is 2 minus 1, which implies 1. That means L can be 0 and or 1. Does that make sense? So the L definitely depends on N. So if N equals 3, we're going to go over all the details. I'll just wait a minute until you write down those. Okay. Now what does those L equal, for example, when L equals 0, L equal 1, L equal 2, and L equal 3, what does those mean? When I say L equals 0, that corresponds to an S subshell, and I'm going to show you the shape of that S subshell. When I say L equal 1, that corresponds to a P. The principal is called the subshell principal. And L equal 2, it's D. And this comes from diffuse, the subshell diffuse. And L equal 3 is the F subshell fun. So what you need to know is to learn those. That whenever I say L equals 0, that directly should translate to you as an S. When I say L equal 1, that should directly translate to P. When I say L equal 2, or you see L equal 2, that should directly translate to you as D subshell. When I say L equal 3, that's an F. Directly should come to your mind as an F. Okay? So now I'm going to show you the shape of those different subshells, which is L equals 0S. So this is the S subshell. It looks like a sphere, and that is the highest probability to find an electron in an S is in this sphere. This is the highest probability that if the electron is in a S subshell, it's going to be somewhere within this sphere. Now, if it is a P, then the electron, the highest probability is to find the electron between those two, the green and the blue thing that you see. Each one of this is PZ, PX. It's called PX because it's on the x-axis, this is on the z, and this is on the y-axis. So for P, we have 3 kinds of subshells. It is one on the PX, PY, and PZ. For S, there is one of them, which the one that we saw. For D, so those are the D. So one on the x-axis, one on the y-axis, one in between, and the only one that looks a little bit different than the others is this one in here. So for D, there is 5 of them. There is 5 different D subshells. Now for the F, we have 7 of them. And those are the shapes of the F1. That means if an electron is in the F orbital, F subshells, the highest probability is to be in that kind, on one of these kinds of the subshell. Now this website, I have it on the first page. If you want to go back and look at the shapes, you can go back to that. So, now, so we said 0 is S, 1 is P, 2 is D, and 3 is F. Now the number of orbitals in each one of those, so in the S, it's equal to 2L plus 1, so it depends on L. For example, for S, L equal to 0, so the number of orbitals is 1. And this is what we saw. For S, we have only 1 sphere. I didn't show you, for example, 3, 4 spheres. While for P, it's 2L plus 1. The L in this case is 1 plus 1, so 3. So a P subshell has 3 orbitals, which we just saw them. The PX, PY, PZ. Let me just show it to you one more time. So for P, let me go back to this. Okay, so for P, you have 3 of them. 3P, PX, PY, PZ, and this is, so P has 3 orbitals. And later on, we're gonna represent them as 3 boxes. For S, we're gonna represent it as 1 box. And the box means an orbital. Now for D, it is 2L plus 1, so 2 times 2 plus 1, that corresponds to 5. And this is what we saw, that for D, we have 5 orbitals. 1, 2, 3, 4, 5. Let's go to the F. The number of orbitals in an F is 2L. The L for F is 3 plus 1, so 7 orbitals. So this one we're gonna represent it as 1, 2, 3, 4, 5, and the F have 7 orbitals. Okay? So you need to know those. So you need to know, at least you need to know that L equals 0, what does it correspond to? 1, 3, 2, and 3, what does those correspond, each one of these correspond to? And then you need to know this equation and how to use it. The number of orbitals in a subshell is 2L plus 1. Then you know the L for each subshell, and you can know how many orbitals are there. Does that make sense? Okay, so let's begin with, if I have a quantum, we said that L depends on N. So for N equal 1, that means we're talking about the first shell, the closest to the nucleus. L can be any value from 0 to N minus 1, that means 0. What does L0 implies? What does L0 implies? It's an S. So, in the first shell, which is the closest to the nucleus, we have only S subshells. And we put the quantum number, the principal quantum number, and before the S to say that this is the first shell and it has a subshell S. So the number before the subshell that we represent before the subshell is the quantum, the principal quantum number, which is the shell. In which shell are we? Are we in n equal 1, 2, 3? Now for n equal 2, the L can be any value from 0 to n minus 1. So it can be 0 and 1. Why? Because n minus 1 equal 2 minus 1 equal to 1. So in shell number 2, the L equal 0 corresponds to an S. The L equal 1 corresponds to a P. That implies in shell number 2, I have S and P. I have the subshell S and P, both of them. For the S, I have one orbital. We talked about S having one orbital. For the P, it has 3 orbitals. Now let's go to n equal 3. The value of L can be any value from 0 to n minus 1. N minus 1 in this case equal to 2. So it can be 0, 1, and 2 because L can be any value from 0 to n minus 1. So L equals 0, that corresponds to an S. I'm in the third shell, so it is 3S. 1 corresponds to P, that means there is a P in n equals 3. And L equal to, it corresponds to a D, so it is 3D. So in other words, in the first shell I have only S. In the second shell I have only S and P, no D. The first time that there are a D there is in 3, in the shell number 3, which is the third one. So if this is n equal 1, n equal 2, n equal 3. Okay? The first time you see a D subshell is in the third one, on the third shell. Okay, let's do n equal 4. N minus 1 equal to 3, so L can be any value from 0 to 3, so it can be 0, 1, 2, 3. That implies 4S, 4P, 4D, and 4F. Okay? So, does that make sense, guys? Okay, we shall see. So I'm going to skip this because I already did all of those on there. So the third quantum number is ML, and it's called the magnetic quantum number. The magnetic quantum number, it tells me about the orientation, the individual orbital orientation. So ML also depends on L. So ML can be any value from minus L goes to 0 to plus L. So ML depends on L also. Okay, let's take the first case in here for L equals 0. For L equal 1, ML can be any value from minus 1, 0, and 1. So what does that imply? That implies for L equal 1, that's a P subshell, right? So for a P subshell, it's telling me there is 3 orbitals. One have a minus 1 orientation, one a 0 orientation, and the 1 orientation. So in P, we have PY, PZ, and PS. These are the 3 orientations. Now, the hardest part of this is that ML, when ML equal minus 1 or 0, or 1, that doesn't imply, so this is what I usually hear from you in office hours. So if ML equals 0, how come it has an orientation? So that -1, 0, 1, take it as if it is just like numbering an apartment as, okay, this apartment is A1, the other is A2, the third is A4. Or let's rename the numbers. Let's say you're in a door, and then the first apartment, they call it -1. That doesn't mean that it is -1 room. It's called, this room is labeled as -1. The other room next to it, they label it as 0. The room next to it, they label it +1. Okay? It's just a label. That -1 or 0 or +1, that doesn't mean there is -1 orbital, or 0, there is no orbital. Because this is what I hear from you in office hours. Okay, but ML equals 0, there is no orbital. Those doesn't match. Take those numbers as just kind of an address for something, okay? Now, for L equal to, ML can be any value from -L is -2, to +L, which is +2, so it can be -2, -1, 0, 1, and 2. That's telling me that L equal to, that corresponds to a D, that it have 5 orbitals, 1, 2, 3, 4, 5 orbitals. And the address of those orbitals, or what exactly on the door of those orbitals, is -2 for the first one, -1, 0, 1, and +2. Okay, so in here, okay, we already covered that part on the slide before. Now, how many of you are confused? Raise your hand if you're confused. Okay, and that's usual, because this topic is not an easy one to discuss. So the easiest way to think about that, that's not the reality. Whatever I'm going to talk about is just helping you to understand this better, but that's not the reality. This is not how the atom is built. Let's take it this way. Let's say I have a building, okay, and I'm the engineer of that building. And the way that I'm gonna build this building is according to the quantum rules. The quantum rules tells me, okay, I have 4 models of apartment. A 1-bedroom apartment, I'm gonna call it S. A 3-bedroom apartment, I'm gonna call it P. And a 5-bedroom apartment, 1, 2, 3, 4, 5, I'm gonna call it D. And a 7-bedroom apartment, I'm not gonna draw all of this, 7 bedrooms, and I'm gonna call it F, okay? Those are the 4 kinds of apartment I have. Now, according to the quantum rule, so n equal 1 is the first floor, n equal 2 is the second, the third, the fourth. So what I said, okay, for me to know what exactly in first floor, second floor, third floor, I'm gonna say L, which is which apartment I'm gonna choose to put in each floor, gonna depends on n. So n is gonna have any value from 0 to n minus 1. Where for S, L equals 0, L equal 1, and L equal 2, and this is L equal 3. Okay? So in the first floor, I have n equal 1. So L can only have a value of 0. Does everybody agree that for n equal 1, we only have 0 as L? Okay, so for L equals 0, so in the first level of this building, I'm going to put only S. Why? Because this is what my rule that I put implies. Okay? Now, let's go to the second floor. For the second floor, L can be any value from 0 to n minus 1, so it can be 0 or 1. That means in the second floor, I can have a 1-bedroom apartment. Why? Because I have L equals 0, and L equal 1, which is the 3-bedroom apartment, which is P. Why? It's L equal 1, so P. Now, I have a mailing system to this building. I want to send mails to this building. So I need to put address on those doors of these 3 bedrooms. So I'm going to say ML represent the address of each room out there. And it's going to be take a value from minus L to 0 to L. So for P, which have an L of 1, ML can be minus 1, 0, and 1. That means the address on this door gonna be on this bedroom minus 1, 0, and 1. Okay, this is the simplest that it can get. I'm just giving you an example. This is in real life. The atom is not built this way. I'm just giving you an example to make it easier how we think about the quantum, the whole building of the atom. This is the way that we put that. Does that make it better? Yes, no, maybe? Doesn't matter? Okay. So let's go back to this. So as we can see, this is kind of explains what I've been saying a minute ago. For n equal 1, it has only S subshell, and that subshell have an ML equal to 0, which corresponds to 1S. For n equal 2, we have a 2S and a 2P. For n equal 3, we have 3S, 3P, and 3D. So the S subshell orbital is found in every shell beginning from 1 on. The P subshell orbital is found from shell 2 and on. Okay? So this table kind of gives you all what I talked about a minute ago about ML and all of this. Now, and to have this equation we already talked about to know how many orbitals there are in a subshell. Now, what if I want to know how many orbitals are in n equals 3? So the number of orbitals in a certain shell equal n squared. So in this case, n squared equal 9 orbitals. So if I look to the third shell would have 9 orbitals. This is the equation that we use. So what I'm going to do is I'm going to go 2 slides backward to see if there are 9 orbitals on the third shell, or that's not the case. Okay, so in the third shell, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is how many orbitals I have on the third shell. So that equation you can use, again, I'm going to repeat, you can use to calculate the number of orbitals in a shell. To calculate the number of orbitals in a subshell equal 2L plus 1. In a subshell is P, S, D, F. This is the equation that we use to calculate how many orbitals in a P, in an S, or a D, or an F. To calculate the number of orbitals in a shell, that means n equal 1, n equal 2, n equal 3. We use this equation, which is n squared. Okay? So now what we're going to do is, I think, a couple of eye clickers, because that's going to help you understand better what's going on. So let's start with the first one. A particular orbital has n equal 4 and L equal 2. What must this orbital be? I'm going to stop it at 1 minute.
Megan.
have the highest percentage for D. D is the right answer. So, first of all, N equal 4. That's the number that I put before the subshell, so it's going to be 4. L equal 2, we know that L equal 0 is S, L equal 1 is P, L equal 2, that corresponds to a D. So those two quantum numbers corresponds to 4D, which is number 2. Okay, let's do this one. Which of the following is correct? And definitely according to the quantum theory that we learned about. Okay. So I'm going to stop it right here and check what you think. So I have C. C is the right answer. So let's see how come. So for A, L equals 3, L equals 3, that's not acceptable. The L can never be equal to L, according to the quantum theory. L can be any value from 0 to n minus 1. So the highest value of L can be n minus 1. It can never be equal to n. For n equal 1, there are S and P subshell. That's wrong. We learned that in n equal 1, we have only S. For n equal 2, we have S and P. For n equal 2, there are only S and P subshell orbitals. That's right. The total number of orbitals for a P subshell is 4. That's wrong. We said that the number of orbitals in a subshell is 2n plus 1. The P equal to 1. The L equal to 1. That means 2, 1 plus 1 equals 3. Or you can even memorize it or know it for sure that P has always 3 orbitals. Okay, so that makes C the right answer. Let's do one more. And this is a numeric, so I'm going to put 1, 2, 3. Again, I'm going to stop it at 110. All of the following sets of quantum numbers are allowed except
Megan, 3 as well. Because of the ML. Right? Isn't the ML on 3 screwed up because it can only be plus or minus L?
So you're supposed to like put them both in there?
Yeah, I think you just set it as 13.
That's weird.
It's kind of silly, but...
okay. So I'm going to stop it right here. So I have 1 to be 39%, 1, 3, 23%. 1, 3 is the right, are both the right ones. So let's check how come. So n equal 1, L equal 1. It is impossible for L to be equal n, so this is wrong. N equal 3, L equal 2, that looks Okay, because L can be any value from from 0 to n minus 1. ML can go from any value from minus L to 0 to plus L, which makes this is right. For n equal 4, L equal 3, ML equal 4, ML can never be greater than L. ML is any value between minus L and plus L. L is this, in this case, is a 3, so that's make this a wrong set of quantum number. So n equals 6, L equal to ML equal minus 2, that's obey the quantum rules. So we're gonna do one more. You know what? I'm gonna leave it for the next time. It needs some time to do this. So I'll see you on Friday.